This is a whole body pressure plethysmograph. It's designed to contain one speaker, and crucial in the design characteristics are that it hold the person comfortably without too much extra space, that the walls be completely rigid and non-yielding, and that it be airtight. So we made ours out of 1.5 steel drums, and it has the following design characteristics. We added a lip at the bottom to increase the stability. Here's the two parts of the two different steel drums welded together. We also added a lip at the top to mesh with the lid. The lid is attached with quick release levers, and the lid itself is plexiglass so that we can see the person can see inside. There's a face mask through which the subject breathes external air, so that actually the ultimate seal between the body of the person and the outside is around the nose and chin area made by the flange of the face mask. So this shows how the plethysmograph works. This is schematically the plethysmograph. This inner ellipse is the speaker, and of course the speaker is connected to the outside through the face mask. This simulates a pressure transducer. So when the person is at the end of an expiration, most of the lung volume is at its minimum. There's a low pressure developed in the air around the person, so the pressure is low. When, however, the person is at the height of breathing in, has taken the greatest inspiration, their total body volume increases, particularly the chest, and that puts greater pressure on the air around the outside, so a greater pressure is developed. Now scoot down as far as you can. Okay, and hug your knees. Okay, so now up we go. Okay, you can stand up now. Let's see. Let's put this one. All right. Should turn around the other way. Okay, comfortable? All right. Now we put the lid back on. Maybe you want to duck now. Okay. Now we tighten the lid. And it's very important to have a airtight seal. And if there's any leak detected, a little bit of Vaseline will help out. Okay, now we connect some air pressure tubes. These are quick attaching valves which maintain complete airtight seal. Are you comfortable?
Fine.
Okay.
A little bit hot and muggy in here.
It's going to be hot and muggy inside, but it will only last for a short time. Say the first few words. You drew will near.
You drew will near. You drew pill near.
Again.
You drew will near. You drew pill near.
Can you try some Hindi? E-B.
E-B.
Again.
E-B.
All right, good. Okay, I'll now attach the pneumotachograph so we can measure airflow. All right. Okay.
you drew will near.
Okay.
You drew pill near.
Okay, good. Now we're going to try something different. We're going to try to measure subglottal pressure. And this requires you to remove the face mask. Okay. Oops. You can just, you can hold on to it. And now hold your hand over the hole. Okay, so you're now breathing a closed system. So whatever air you take in under pressure leaves lesser pressure on the outside. And as you breathe out, reducing the pressure in the inside, you're augmenting the pressure in the air around you. So now say pin twice and so on. Okay. Let's let you have some fresh air. So, feel better?
A little bit. I like the draft.
Yes. So here we have the plethysmograph signal at the top and the airflow signal at the bottom. These are averages of 10 tokens. And the synchronization point for the averages was the release of the D in this sentence, you drew will near. Of course, this is a funny sentence designed just to have mostly sonorants, just has one stop in it. This is the point where the pressure, the lung volume changes from being increasing to decreasing, of course, is the start of the expiration on which speech is superimposed. Of course, it generally shows a downward trend because speech is made on an expiration. So the airflow signal shows a decrease in airflow during the closure of the D, and then a sudden increase upon its release. Corresponding with that, we can see a slight plateau, a slight leveling off of the lung volume decrement at the moment of the D. Otherwise, it's fairly smooth. At the end of speaking, you usually have more air left in your lungs than you need. You expire it, and it comes out in high volume, and at that point the lungs start a kind of passive collapse and then move on into the breathing in, inspiration. So this is the sentence, you drew pill near, and the interest here is of the what happens during the aspirated stop. Of course, again, the airflow shows a decrease during the closure, and then a huge increase in airflow upon the release of this stop since it's aspirated. And again, during the closure, there's a slight plateau in lung volume decrement, and then during the moment of aspiration, there's a steep decline. So I view this as a passive collapse of the lungs during the aspirated stop. And here's when Priscilla was simulating some Hindi stops, E-B. It shows much the same character for the lung volume curve as it did for the voiceless aspirated stop. A sharp decrease upon the moment of release, which is where the aspiration occurs. In this case, we've also taken the first derivative of this curve. And that's what this is. Again, averages. And turns out that this curve pretty much, if we may use this curve from the voiceless stop, that the airflow curve pretty much is a mirror image of the differentiated lung volume curve. Okay. Okay. Now, if you want to have those newspapers here.
In our speech production laboratory here at the University at Buffalo,
We collect aerodynamic as well as respiratory kinematic data produced during speech. Our primary goal is to describe and investigate children's speech mechanisms with an emphasis on the laryngeal and respiratory systems. In order to do this in a relatively non-invasive way, we use several sensing devices that the children really tolerate quite well. The first device is called a pneumotachograph mask and is used for sensing airflow. This particular mask design can be described as being circumferentially vented and was developed by Martin Rothenberg at Syracuse University. As you can see, it's made from a standard respiratory face mask which has a series of holes punched around the circumference of the mask. The holes are covered by a fine wire mesh, and that presents the slight resistance to the flow of air through the mask. The resistance causes a pressure differential which is proportional to the airflow through the mask. Right here is a pressure tap that's also a port to the air pressure transducer, which is mounted right on the mask. This particular transducer has a wideband frequency response in that it picks up higher frequency flow components than most typical air pressure transducers. It's because of this response that it produces a waveform that looks very much like a voicing waveform. Notice that we have a second pressure tap which leads to a second transducer with a lower frequency response. It's from this transducer that we generate the average airflow and the volume waveforms. The third tap on the mask, right here, is connected to another pressure transducer optimized for measuring intraoral air pressure. Inserted inside the mask at this tap is also a small hollow polyethylene tube that will be placed into the oral cavity and picks up the intraoral air pressure values. Now I'm going to demonstrate how we calibrate for airflow, air pressure, and air volume. To calibrate for the airflow, we place the pneumotachograph on the mold. While using a device called a rotometer to indicate the flow moving through the mask transducer system, we record this signal and use it for later reference. We calibrate for airflow for each mask size that we use. So this is the medium-sized mask, and this is the one that's used for adult females and teenagers. We use the large size mask for adult males, and this is the small size mask that's used for the younger children. When calibrating for intraoral air pressure, we use a device that's referred to as a U-tube water manometer. By displacing the water column and measuring the distance that the column moves on each side, we can express the subsequent pressure measurements in terms of centimeters of water. We record the calibration signal produced and use it for later measurement. Our next calibration procedure is for making the volume measurements. By not having our subjects breathe into a respirometer to calibrate for volume, we don't fatigue them with an additional calibration maneuver. This has been especially helpful when working with the children or with hard-to-test patients. This time we connect the mask on the mold to the respirometer, and we repeatedly displace 2 liters of air through the mask. We digitally integrate this cyclic flow signal and then scale our low-frequency flow channel. This allows us to calculate the volume displacement by integrating the flow signal. This brings me to the last piece of equipment that I'd like to demonstrate, the linearized magnetometers. This is just a brief deviation from the aerodynamic techniques that I've already presented. But since we use this quite typically with our aerodynamic techniques, I wanted to present it at the same time. The magnetometers have been used for quite a while, and you can look at Hickson and Hoyt-Hickson for further detail. Linearized magnetometers operate in pairs. There are 2 pairs for sensing the chest wall movements, one for the rib cage and the other for the abdomen, so that when attached to the front and back of the abdomen, they will track the movement of that part of the chest wall. Here, I'm just going to demonstrate the movement of the abdominal pair. The emphasis on this demonstration so far has been on speech aerodynamics, and now I'm briefly going to demonstrate just how we collect the simultaneous respiratory kinematic data from unwilling but well-paid children. Here's a segment from a tape made of Nick, my son, performing the pa-pa-pa task. We've already attached the magnetometers to the chest wall. We've got one pair attached to the rib cage and the other pair attached to the abdomen. Turn around, Nick, so that we can look at that. All right, now turn around this way. And what we're going to do next is have Nick sit in a chair, and then we'll look at how we pair the aerodynamic equipment with the respiratory kinematic equipment. We're ready to put the mask on Nick. Before we start, I'd like to point out that we've got this part of the mask which would hit the bridge of the nose built up with a little bit foam on the inside, because very often we get a leak in this area and we want to make sure there's not a leak during the task. Okay, Nick, I'm going to put this on your face. I'm going to kind of smush it on hard, and then I want you to put the tube in your mouth like you would a straw, right behind your lips and behind your teeth, and then you'll just talk around it. And you're going to say that pa-pa-pa task for me, okay?
All right.
Okay. Ready? Go.
Pa, 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 pa.
Okay? Okay. You're going to say 7 of those. I want you to make them all connected. And I want you to make a nice pa. Not a ba, but a pa. Okay? Ready? Go. Pa, 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 pa. All right. At this point, we would work with the subject. We would make sure that the number of syllables were the correct number, that there was a tight seal around the edge of the mask. Let me just take this off. That we had appropriate pressure waveforms, and that generally things are just the way we want them. We'd try to get 3 trials for this particular task. Then if we wanted to do some inverse filtering, we might have Nick phonate an ah or an ah and look at inverse filtering during a sustained vowel. And all the while that we're collecting the data, as I said before, we'll check for leaks and for the appropriateness of the task. And that's it. Now let's take a look at some of the waveforms that were produced by that session. The first waveform is the wideband airflow signal, which includes voicing. It starts off with rest breathing, indicated by the slower alternations, and then proceeds into the speech task, pa, pa, pa. The second waveform is the low-frequency airflow waveform, also called average airflow. Next is the intraoral air pressure waveform, which demonstrates the pressure variations as the subject is saying pa, pa, pa. It's from these 2 waveforms, the average airflow waveform and the intraoral air pressure waveform, that we make estimates of laryngeal airway resistance, a la Smitherin and Hickson. The fourth waveform represents the subject's lung volume, which is the result of the integration of the average airflow. The fifth and sixth waveforms show the movement of the rib cage and the abdomen. On each of these last 3 waveforms, the lung volume waveform, the rib cage, and the abdomen, we can look at where the speech utterance was initiated and where the utterance was terminated. Finally, there's the voicing waveform, which has been calibrated for sound pressure level and is used for SPL measures during the speech tasks. Let's take a closer look at the top airflow waveform. Here we have expanded the mid portion of this vowel. This signal came from the wideband pressure transducer and includes the fundamental frequency as well as the formant frequency information. The bottom waveform on the figure shows the oral airflow waveform after it's been inverse filtered using C-Speech, a computer program developed by Milenkovic. It's now depicted as a glottal airflow waveform, and it's from this waveform that we make a variety of measures, such as approximations of how long the vocal folds are open relative to the duration of the cycle, the speed at which the airflow shuts off, the constant flow that may be present due to something like a posterior opening between the vocal folds during the closed part of the cycle. Previous research in this area has been published by scientists such as Holmberg, Hillman and Perkel, Goffin and Sundberg, and Tietze. I'd like to finish by restating that the emphasis in our laboratory has been the simultaneous measurement and interpretation of laryngeal and respiratory function. We primarily work with children using aerodynamic and respiratory kinematic techniques. There are, of course, a variety of ways that you could use these techniques clinically. For example, if we wanted to help evaluate the speech of someone with a cleft palate, we would enlist the aerodynamic techniques for looking at nasal flow and intraoral air pressure. If we wanted to use the procedures with neurogenically impaired individuals, we might use the respiratory kinematic measures to evaluate respiratory function, as well as the aerodynamic techniques to help quantify velopharyngeal function. We might also use a combination of measures to evaluate and help plan a voice evaluation. We could study and quantify vocal intensity, fundamental frequency, and glottal airflow measures. Lastly, the system is flexible. A clinician can decide what to do based on each patient's needs.
An accurate physical description of speech production requires precise measurements of moving air and tissue. This video demonstrates how these measurements are collected and how these properties fit together in a mathematical model. The elastic properties of laryngeal tissues are quantified by stretch-release experiments. Laryngeal tissue is mounted in a double-walled glass chamber containing a physiologic solution as demonstrated by Dr. Young Min. Water is circulated between the double walls of the glass chamber to maintain the tissue at body temperature. Perfusion provides proper oxygenation to the tissue during the experiment. At the bottom, the tissue sample is secured within the chamber. At the top, a servo-controlled cantilever arm provides mechanical stimulus to the tissue. With this arm, specified elongations or forces can be applied to the tissue in a stretch-release pattern. The data are recorded automatically by computer, and the entire cyclic stress-strain curve can be plotted immediately after the experiment. These data provide the basic information for elastic properties of vocal fold tissue. The experiments can be done on the cover of the vocal fold as well as on the ligament and muscle. Pressure flow events are quantified by conducting experiments in a scaled-up model of the glottis. Once key measurements have been made, the Navier-Stokes equation is solved to numerically supplement any information that cannot be obtained empirically. A long fluid channel conditions the air so that the flow in the subglottal region is laminar and can be analyzed in a two-dimensional profile. Pressure levels are recorded in the subglottal, glottal, and supraglottal regions using fine taps that are drilled into the static vocal fold configuration. In addition, hot wire anemometers are used to measure the velocity profile of the air. Dr. Fari Alipur takes measurements to quantify airflow through the glottis and the pressure flow relationships. This includes quantification of vortex shedding, turbulence, and instability in the jet stream. Once the fundamental constitutive equations for tissue and air movement have been established, it is important to quantify the geometric shape of the vocal fold. First, Brad's story demonstrates how a reasonable representation of the prephonatory glottis is made. Silicone is injected into the glottal space of an excised larynx and allowed to harden, producing a mold of the glottal airway. Molds are extracted and sliced into various layers to get geometric measurements of the glottis in the superior-inferior direction and the anterior-posterior direction. Using measurements gleaned from the mold, the glottis is modeled with a mathematical formula. We have found it appropriate to model the lateral surface of the vocal folds with a parabola and the anterior-posterior variation with a straight line. Next, stroboscopy is used to quantify the modes of vibration in the tissue, including amplitudes of vibration as a function of subglottal pressure and fundamental frequency. A large data set has been developed which shows how amplitude and frequency are affected by vocal fold elongation and lung pressure. The modes of vibration are simulated by computer. Three-dimensional graphics allow the model to be viewed from different perspectives. A primary objective in physiologic modeling of laryngeal function is to show how intensity, fundamental frequency, and quality in phonation change with various muscle contractions. Dr. Harry Hoffman places hooked wire electrodes into the laryngeal muscles with a hypodermic needle after local anesthesia. The mic-to-mouth distance is measured so that sound output levels between subjects can be compared. The subject then executes an extensive set of vocal exercises. When measures of subglottal pressure are needed simultaneously with cricothyroid and thyroarytenoid activity, a tube is placed into the corner of the mouth to measure oral pressure in a bilabial consonant-vowel sequence. In this manner, subglottal pressure can be estimated from oral pressure in techniques that are described in literature. An important graphic representation of the results of these experiments is the muscle activation plot, which shows cricothyroid activity versus thyroarytenoid activity with subglottal pressure as a parameter. Constant fundamental frequency bands are drawn that indicate the combinations of various activities that can produce the same fundamental frequency. The next step in the modeling process is to compare simulated glottographic signals with those that can be measured non-invasively. Specifically, mouth airflow and electroglottographic signals are used to validate the model. Kenneth Tom demonstrates how simultaneous measures of mouth flow and EGG are taken. The signals are displayed in real time on an oscilloscope and later digitized for examination and processing. A similar series of combined waveforms simulated by the model is compared to measured waveforms. An optimization procedure is used to match the two sets of waveforms, thus refining the parameters of the model. A final step is needed to validate the model. Here, vibratory modes in human subjects are contrasted with those produced by the model. The best results from human subjects are obtained with a rigid fiberscope placed into the mouth toward the back of the throat, as Eileen Finnegan demonstrates. It is possible to make measurements of vibrational amplitude and, to a limited extent, mucosal wave propagation and vertical phase differences in the movement. It is also possible to see higher-order modes that may occur due to peculiar excitations. Wireframe diagrams and animations provide a means to study modes of the model in detail.
Once a simulation model has been validated, we have a rich new medium for experimentation. In fact, the model itself becomes a new laboratory. We're currently using the model to study phonosurgical procedures, to study voice disorders, to distinguish between artistic and normal vocal productions, and to study control of pitch, loudness, register, and voice quality in speech. The beauty of a simulation model is that you can't break it, and it doesn't deteriorate, and no human subject or animal is at risk in the exploration.
Okay, are you ready to start again today? Good. We're going to do the same thing as last week. All right. We're going to work on the phrase, how are you? All right. We'll do it 2 times. All right. The first time we're going to emphasize are. How are you? The second time we're going to emphasize you. How are you? Okay? Good. Put that on again today. Ready? Okay.
How are you? How are you?
Good. Let's
This
try it
deaf
again.
college student is working on improving her voice using a device called the electroglottograph,
One more
or
time.
EGG.
How are you?
The EGG permits non-invasive examination of time-varying changes in vocal fold contact during voice
How are
production.
you?
This easily obtained, physiologically based measure can provide clinicians and researchers with useful information about vocal fold morphology and physiology that augment less direct acoustic measures or more invasive techniques such as direct laryngoscopy. The purpose of this video is to show how the EGG is used both for research and in the clinic. The principles of operation will be described, along with a general description of how the device is positioned and adjusted. We will also examine the parameters of the EGG waveform and how the EGG has been used in the laboratory and in the clinic to examine certain aspects of vocal function. The principle of electrolithography, in which the amplitude of an electrical carrier signal is measured, has been around for over 50 years. In 1940, Philip Faber published an article on a new method for monitoring the arterial pulse frequency in the area of the carotid artery. In 1957, Faber described the first application of this technique for examining voice production. This videotape will demonstrate two commercially available devices. The first system was developed by Martin Rothenberg of Syracuse University and is marketed by Glottal Enterprises. The other device was developed by Dr. Adrian Forson and is marketed by Laryngograph Limited. All EGGs are comprised of two basic components. First, there are the electrodes. The electrodes apply to the neck a small, physiologically safe, electrical carrier signal in the 1 to 5 megahertz range. These wires connect the electrodes to a second component, the processor box. The processor contains electronics that generate the carrier signal and that measure small modulations in that carrier signal that are caused by the voice. These modulations in the carrier amplitude are what we define as the EGG signal. The box also contains filters, amplifiers, and other components that optimize the signal for display and for analysis. To attach the EGG to a subject, I'll position the electrodes on the neck, one on each side of the thyroid cartilage. To ensure good contact between the electrodes and the skin, a small amount of water-soluble electrode paste is applied to each of the electrodes. The electrodes are first positioned on the neck in the general region of the vocal folds and can be held in place with the two fingers or with this strap. I'll use the strap here. Good. The position of the electrodes relative to the vocal folds determines the strength of the signal. Could you say ah?
Ah.
Okay. I'm moving the electrodes up and down a bit until I get a good strong signal. Try it once more. Once more. That's good. EGG signal strength is monitored on the meter of the device, and I can also use an oscilloscope to determine the position that yields the greatest output signal. A small percentage of subjects' EGG outputs are too weak to be usable. The strength of the EGG signal is determined by the person's neck anatomy. Those subjects having thinner necks and more prominent thyroid cartilages tend to have stronger EGG signals. The signal strength meter on this device can be useful in determining whether the EGG signal can be relied on as a measure of vocal fold contact. The amount of vocal fold contact occurring during each glottal cycle changes cyclically. This slow motion film shows the folds alternating between being fully separated and fully together. Notice that after the folds first make contact, they continue to approximate along their vertical dimension and then begin to separate. These cyclic changes in contact area between the vocal folds occur from the bottom to the top, resulting in the undulating movement that characterizes vocal fold vibration. The cyclic variations in glottal area are shown in this typical trace. We can see the relationship between changes in glottal area and the other signals we've examined by adding them to the display. In the trace polarity shown here, upward movement of the EGG trace indicates an increasing amount of vocal fold contact, while a downward deflection of the trace shows diminished vocal fold contact. This type of display is called the vocal fold contact area signal, or VFCA. It is sometimes easier to interpret the signal if it is inverted, so that the top represents less vocal fold contact and the bottom represents more contact. This orientation makes it easier to compare the signal to the flow glottogram, for example. When the trace is inverted, we refer to the display as the inverse vocal fold contact area signal, or IVFCA. A switch on this device permits the user to choose either polarity. We can divide the EGG signal into a few time phases corresponding to when the vocal folds are apart, approximating, or separating. Notice that during the time the folds are approximated, the signal is changing. This is because the amount of vocal fold contact continues to increase after initial contact is made. Contact area increases until the folds are most approximated, and then the amount of contact begins to decrease. Also notice the flatter portion of the trace, when the vocal folds are not in contact. Although the distance between the folds is changing, there is very little change in the amount of contact between them. Since it is primarily the contact between the vocal folds that affects the electrical resistance seen by the electrodes, the EGG signal changes very little during this portion of the cycle. Thus, there is little information conveyed by the EGG signal about the open portion of the vibratory cycle of the vocal folds other than the duration of this period. The EGG has been primarily used in the laboratory. Perhaps its most common use has been for detecting vocal fundamental frequency. It's a good signal for this purpose because it has a strong fundamental frequency component, thus permitting determination of fundamental frequency using a simple threshold crossing, zero crossing, or peak picking schema. Unlike acoustically based strategies for extracting fundamental frequency, the EGG does not change significantly for different vowels, thus providing a much more constant waveform for extracting fundamental frequency. The EGG signal has also been used to examine the extent of abduction or adduction during voicing. A person speaking with a breathy voice quality often has EGG signals whose contact duration, the part of the glottal cycle during which the vocal folds are together, is greatly reduced as compared to normally voiced productions. The systematic changes in vocal fold contact associated with the overall abduction or adduction of the folds has been examined for stutterers, for deaf children, and for normal hearing speakers. An additional feature of this EGG system permits fairly precise positioning of the electrodes and monitoring of laryngeal height. Each electrode disc is actually a pair of electrodes, one above the other. This results in two EGG signals being generated. When the amplitudes of both signals are equal, it means that the electrodes are positioned vertically with the vocal folds exactly between the two pairs. This can be useful for positioning the EGG on different subjects in approximately the same vertical location. An additional advantage to this twin electrode arrangement is that as laryngeal height changes during voicing, the relative amplitudes of the top and bottom pairs of electrodes will change. The ratio of signal amplitudes is converted by the processor to a signal that monitors laryngeal height. This specially designed calibration device permits quantifying the laryngeal height signal in centimeters for each subject. The laryngeal height feature has been used to examine the singing voice and deaf speakers' control of voice. Let's now look at the other EGG system shown earlier, the laryngograph. This device is available with a computer interface card and a set of programs that enable display and analysis of the EGG signal using a PC computer. One of the displays in the software package provides a visual representation of fundamental frequency obtained from the EGG signal against time. The split screen displays a template or model on the top and provides the learner with feedback of the fundamental frequency of their attempt. This type of display is useful for both deaf clients and for those learning a second language. A second display permits analysis of the speaker's fundamental frequency characteristics during connected speech. After acquiring the EGG signal for a period of time, the software displays a histogram of the fundamental frequency distribution together with statistics that characterize the distribution. This feature is useful for diagnosis of fundamental frequency-related voice problems and for monitoring changes in average fundamental frequency associated with therapy. The next display shows the actual EGG signal either alone or in combination with other signals, such as the acoustic signal from the microphone shown here on the top trace. This provides a means for both the researcher and clinician to examine changes in glottal waveform characteristics associated with different vocal pathologies or disorders. For example, It is useful for examining and quantifying EGG attributes associated with production of breathy voice productions or associated with articulatory gestures of the vocal folds for consonant devoicing. In this brief program, we've seen that the electroglottograph provides a potentially useful way of viewing vocal structures. The changes in vocal fold contact, viewed either alone or in combination with other signals, such as the flow glottogram, can provide useful information about fundamental frequency, vocal fold contact, and laryngeal height. While the device has limitations, it can prove a useful supplement to existing research and clinical instrumentation.
The human voice is a unique instrument that serves basic needs of communication. While we are used to listening to the voice and can easily make acoustic measurements of the voice source, actually observing the vibrations is difficult due to the inaccessible position of the larynx. Hence, specialized equipments and techniques are needed in order to visualize what's going on in the larynx. One piece of equipment is the rigid endoscope. It's a cylinder with an optical system inside. At one end is a lens that allows viewing objects at an angle to the endoscope. At the other end is an attachment for a camera and a light source. The endoscope is attached to the light source and to the camera. The tongue is pulled forward during the recording to get a clear view of the glottis. Recording laryngeal vibrations using a rigid endoscope thus prevents normal articulation and can only be used during sustained phonation. For clinical examinations, this is usually sufficient. The view through the endoscope shows the interior portion of the larynx at the bottom of the screen. At the top of the screen are the two arytenoid cartilages that move to adduct and abduct the vocal folds. The white spot on each vocal fold close to the arytenoid cartilage is the vocal process. In normal light, the view of the vibrating glottis is blurred.
Normal pitch. High pitch.
In stroboscopic light, the individual vibrations can be observed. Another instrument for laryngeal observation is the flexible fibroscope. It consists of a bundle of thin glass fibers that transmit light and images. The fibroscope can be inserted through the nose and thus does not impede normal articulation. The fibroscope is connected to the light source and to the camera. Before the insertion, an anesthetic and decongestant can be sprayed into the nasal cavity. During breathing, the glottis widens during inspiration and narrows during expiration. The mode of the vibrations is controlled by varying the degree of adduction of the folds, less adducted for breathy voice and more adducted for pressed voice. The fundamental frequency of the voice is controlled by changing the tension of the folds. The length of the folds increases with tension and fundamental frequency. EP, EB, EC. During speech, the voice source must be turned off for the production of voiceless consonants. This is done by opening and closing the glottis at the appropriate times. EP, EB, EF, EV, EC, EHE. An outside view of the larynx shows light passing into the trachea when the glottis opens between phonations. A light sensor placed on the neck below the glottis converts variations in light passing through the glottis into an electric signal. This technique is called transillumination. The insert shows the output from the light sensor. Increasing glottal opening is displayed upwards. E, 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 EP, EB. The transillumination technique is particularly useful for recording glottal abduction and adduction during voiceless consonants. Here it provides information on the timing of the glottal gesture. For obvious reasons, the signal cannot easily be calibrated. EHE, EP, EB, EF, EV, EC, EHE, EP, EB, EF, EV, EC. Transillumination offers a useful tool for studying the coordination between oral and laryngeal articulatory movements. In this experiment, transillumination is used to record glottal movements. Small, light-emitting diodes are placed on the lips and on a jaw spline to record movements of oral articulators. The diodes are tracked by a special camera. This experiment also involves applying a mechanical load to the lower lip during speech. A paddle rests on the lower lip. The paddle is connected to a motor that can be activated to pull the lip downwards. The motor is operating under computer control so that the load can be applied to the lip when the subject is making the oral closure for a bilabial stop.
Go. Let's add that one.
The rationale for this research is that the nature and time course of the responses to the load can reveal the motor organization and reflex structure of the motor act. The view of the glottis is monitored during the experiment to make sure that there is a free passage for the light from the fibroscope to the glottis.
Go. What's out that boat?
Studies using this experimental paradigm show that when the lower lip is perturbed, the upper lip and the jaw compensate for the perturbation so that the bilabial closure is still achieved. However, it appears that the timing between the larynx and the upper articulators is affected by such a perturbation.
No perturbation on that trial.
Go. What's out that boat? Go. What's out that boat?
No perturbation on that trial.
Go. What's out that boat? Go. What's out that boat? Go. What's out that boat?